Okay, we're in Chapter 11 still, and this is part 3. This is the third type of model that we're going to deal with, and we're going to call this the economic analysis of waiting lines. The cost for the waiting lines, the cost of what it takes to run a waiting line, the cost of what's valuable to our customers, and so on. So here's an example. This company, the stock trading company, was very successful. Business doubled. Now the orders are arriving at 40 per hour. They've got to decide how many traders to employ. And again, each trader can process in an average of 2 minutes time. So the trading company has to determine, well, what's it not only going to cost us to have the traders, what's it going to cost us if there are delays? So in processing orders. So they consider a lot of things. They've determined the average waiting cost per minute for an order is 50 cents. That is, if there's a delay per minute, cost per minute. And we can run through a comparison, the cost of hiring 2 versus 3 traders. So what would that look like? Well, again, I'm not going to go through the details here. We can do this in our models, in our MM1 or MMK models. But in this case, we've got to calculate L, total hourly cost, for when K is equal to 2 or K equals 3. Lambda is equal to 40, mu equals 30. We know that. If we were to run through that math, we would get the cost of 2 servers. The probability of nothing in the system, P sub 0, would be 0.2 or 1 over 5. We're going to use Excel. We have that. Once we have that value, knowing the rest of our values, we can calculate the total cost at $30 an hour. And then again, we've given this on a per minute basis, 50 cents per minute. Okay, so again, we had a rate here of $112 per hour. But again, using Excel, we can do this very, very simply. We can do a comparison to the cost of 3 servers, get $104 an hour. We're going to make a little table. We can actually see the total cost per hour for having a 3rd trader is actually less expensive than having 2 traders when we consider the implications of the waiting costs for our customers. So again, here let's consider something else, an analysis, and there will be a question on the next test, on Chapter 7's test. In this regard, we're going to do a comparison between an MM1 and an MM2. So the answer to this is broken down here in the it's more Chapter 11 practice problems with answers file. But this company is considering opening a 2nd service counter. They currently have 1. Arrival rate lambda is 10 per hour. Service rate mu is 14 per hour. Cost of waiting is $30 per hour. The cost of each service counter is 22. Should they open a 2nd counter? So let's look at this. Okay, so let's walk through this. What we have to do in this example is to do a comparison between the cost per hour of an MM1 and in this case an MMK model, but where K equals 2. So given this lambda of 10, this mu of 14, cost of waiting of 30, cost of service is 22, I've already populated the 2 models. I pulled down the MM1 model here. I populated 10 and 14, make sure I put per hour so I know they're in common units. I populated cost of waiting is 30, cost of service is 22. I get a rate of $97 an hour when using a single server, single line. Let's look at the MMK. I've already, again, pre-populated some of this prior to showing this to you. Number of channels is K is 2 in this case. Arrival rate and service rates are the same. But now we have to look at the ratio of lambda to mu, and we have to complete this cell C15, cell for students to enter. It's green. We derive that from table 11.4, and I'm going to round a little bit. And when I give you examples, we can interpolate between 2 values on the table, but for this example, I'm just going to round. When I give you a question in the test, the values of the ratio will be nice round numbers that will correlate to that table perfectly. But in this case, let's just round this down to 0.70. In that case, if we go to table 11.4, the leftmost column, the ratio is 0.70. Then we go over to the right. K equals 2. It can be 2, 3, 4, 5 in this table. K is 2. The value of P sub 0 is 0.4815. You have to do this. You need to do this in order to get the correct answers. We enter that value, 4815. The cost of waiting, we're told, is 30. The cost of service is 22. In this case, we get a value of 68.61 per hour. So the fact is that answering this question, should they open the second counter? Well, the answer is yeah, because for when K is 1, it's $97 an hour cost. K is 2, it's $68.61 per hour. So it's actually less expensive and more attractive to have a second line so their customers do not have to wait. All right, there will be a test question be very similar to that. All right. 3 more types of models, and they're all pretty straightforward and simple. And let's start to walk through them. I'm calling them type 4. We have constant service times, not variable service times. It's not represented by a distribution. It's constant. We know what it is. So instead of MM1, it's an MD1. Examples would be automatic car wash, some ticket dispensers, maybe a vending machine. You know what the service time takes. Here's an example, a pony ride at a given store, 2 minutes for a certain amount of money. Children arrive at a rate of 15 per hour. Well, here's another question, definitional thing, and I want you to grasp this as well. If lambda is 15 per hour, we're told that they arrive at a mean rate of 15 per hour. What is the service rate? If it takes 2 minutes, we can do 30 of them in an hour, 60 divided by 2. Utilization in that case is being used half the time. Utilization, again, is lambda over mu, 15 divided by 30, so half the time. The idle fraction, I mentioned this term earlier, the idle fraction is 1 minus the utilization, so it's also idle half of the time. So how would we calculate some of the other values in terms of waiting, so on? You can use these types of formulas, or you can use Excel using the single line constant MD1 template, and it's a lot easier. So I will ask you some questions using this template, but it's pretty straightforward once you plug in the values. So here's a practice problem. Again, the answer is also out online. Arrivals at a box office for a show, followed by Poisson distribution, that's an M, lambda equals 7 per minute. Service times are 7.5 seconds. Aha, notice that these are different units. So we're given the arrival rate of 7 per minute. I'm going to convert this to also to minutes, the service rate. If it takes 7.5 seconds to do something, how many of those somethings can I do in a minute? It'll be 60 divided by that value. So I can service 8. I can service 8. So this answer is for any of the L sub Q or W, whatever it might be, are easily developed using the MD1 template once we correctly identify lambda and mu. So see the more practice problems Word file for a little more detail. All right, the 5th type, 5th of 6th, arbitrary service times. We have a G, we call that a G variable. So again, in this case, there's an example here for self-service copy machine, 12 customers per hour, arrival rate, and a normal distribution of 2.5 minutes, but there's a deviation. There's a variation in that. Again, it's an arbitrary. It's not known, it's not fixed, and it doesn't have a Poisson distribution. It has some variation around a mean. So if I convert these, if I get a common lambda and mu, I express these in per minute basis. I have sigma. It's expressed in the standard deviation of 30 seconds. And so we can convert that to minutes of 0.5. Okay, so we can calculate again manually, or we can use Excel to calculate this using the MG1. Once we know the values for lambda, for mu, and for sigma, we can plug those in. Look at the MG1 model. Okay, all right, so again, here's an example, telephone service system. Lambda, mu are given, sigma is given, find in the units per hour. Okay, we can calculate any of these. So enter those given values into an MG1 model. All right, last type. All right, type 6, the last one. Waiting lines where we have a finite calling population. That is, we know that there are only a certain number of sources or persons or destinations that can come back and be part of the Q. And we call this model MM1F. We're using a single server, but we call it with the suffix F to designate finite calling population. One thing we need to know is we need to understand the size of that calling population. We call that variable n. And let's see, we're going to let this be where n equals 4. And then we have we have to derive from our language that we're given in our situation lambda and mu. And so let's look at this case. 4 students in a class. That tells you right off the bat that that should be our population. So n is 4. They give a 5-minute summary. Okay. So that's the duration. What's the service? Okay. So 12 per hour. That makes sense. These correlate. And I can do 12. If it takes 5 minutes to do something, I can do 12 of them in an hour. Assume arrival rate is 2 per hour. We can answer any of these questions knowing now that lambda equals 2 per hour, mu equals 12 per hour, and n is 4. Using the MM1F model, make sure you're aware of units, but we can do that, and you can see the answers for this on our More Practice Problems file. All right, end of chapter 11. I think that you should find this pretty straightforward once you master how to convert the lambda and mu into common units. Watch that. Also be wary when we ask for numbers about units of hours, minutes, days, weeks, and so on, that you're using the right units. Be careful with that and pay attention to the details. Thanks very much. Have a good rest of your day. Bye-bye.